So hey, welcome back. So in last video we have stopped here till now, and today we'll for sure will go up to VTC. But before that, what does mean VTC? VTC is your voltage transfer characteristics, and transfer means you are giving some voltage in the input and you are getting some other voltage in the output, so it getting transferred. And how it is getting transferred, if you wanna plot that graph, then that graph is called your VTC. And why VTC is important? Because from VTC you can analyze how your inverter is it a strong PMOS inverter or strong NMOS inverter. What does mean, we will explain. Also noise analysis can be done from the VTC only, so we'll explore everything today. And I'm starting, and you have time to like this video, so let me start. So let me close it. I hope you have done for the PMOS these characteristics things. If not, I will strongly suggest pause this video now and revise the episode to do that and then come here, because these things are incrementally, we are growing together, right? So please don't skip any video and come to other video. So let me close this also, and let me close this also. Okay, so here what I'll do, I will make another file, schematic file with some other different name. So to make any file you need to write touch to make a file, mkdir to make a directory. So touch, and let us give it as inverter vtc.sch. sch the like it's a schematic type, so sch, and then we will invoke our Xschem. So Xschem and then the file name, so it will directly open that file for us. And here we are. So let me quickly draw the inverter, right? If you know how to draw the inverter, then skip to the next position, but let me do it for the people who are still confused to how to do it. So before what we'll do shift I, we'll go to this one. Here inside this we have our NMOS, so NFET. First we'll get a NFET, the simplest one, and the simplest one is this one. So get this here. NMOS is always down, PMOS is always up. Why? Explanations are already there in the interview preparation tutorial series. You see it, and after seeing it, try to do this jumbling. Give your NMOS up, PMOS down, and see what is happening. So actually I have given you the power. Now you can experiment anything which is written in the book for the inverter. They are telling it using their theory, try to prove it using your practical things. So, and that's very nice thing actually. If you are in your first year, second year of BTech, mostly suggested thing, you should do it because you have time. PFET, and for PFET also I'll be using the simplest one, and PFET is there, and then I'll just connect it. And today we'll do the symbol also. We'll create a symbol and then we'll use a test bench to verify this thing. So here let me connect everything. So W connect this thing, and then W connect this thing, no, and then W, and we need like actually any inverter have 4 terminals, right? So the first terminal, this terminal would be your V in. So this is V in and this is your V out. So let me get the pins. So for pins, what you're gonna do, go up inside schematic, like Xschem default, and then left pin, okay, and fix it here, and then select C and do nothing, just move your mouse to get it here. Then again select C, do nothing, move your mouse to come here, and then shift R to rotate it, and then connect it here. Okay, so this is your VDD. After doing this thing, actually we have created the level. Actually here levels is not important because we're gonna create a symbol. So for symbol, the pins are important. These are not pins, these are levels actually. But before that, see, star is there, one star is there, you can see, right? If I zoom in, one star is there, so that means it is not saved. So it is every time when recommended, keep on saving. I also forget, so that's why I keep on reminding you, control save. Yes, so I have saved it. So let us get the pins. So again shift I and again write it here pin. And in pin you have three types: input pins, output pins, and input output pins. There are few times where it is a input also output also, so that time we'll use input output. But for the small project like this doesn't matter, but for symbol it matter. So mostly we'll use input and output pins. So I'll take input pin. Okay, so this V in will be my input. Let us do one thing. It is becoming a little dirty here, so let me delete these levels are not important. Get the shift I, pins, input pins, get input pins here, copy it, and because our BDD will also be input and our ground will also be a input, and the output is our V out. So pin, and in pin I have everything is perfect. I will again save it, control save. Yes, and after that focus. To make a symbol here, what you're gonna do, you just need to press A for apple in your keyboard, A. So I'll just press A and it will show, hey, do you wanna make a symbol? I'll say okay. So symbol got created, but where it is, I can't see any symbol. So actually symbol it got created in the same folder. So to open it, we'll go to the file, open, and and see inverter VTC schematic we have created, and this got created by the Xschem, and that is your symbol SYM. So let me open that one. So this is your inverter symbol, but it is not looking like an inverter symbol, right? So let us create which look like an inverter. So for that I think you can draw a polygon. Polygon. So go here and then let me see. So let us make it and this. Okay, and then what you need to do, you can arrange them anywhere, no issue. Anyway, it's like suitable, like it's easy for you, because why we're making a symbol, because we'll use this symbol to the other bigger cell. For example, we're gonna design a AND gate from a NAND. So AND gate from a NAND means NAND and then an inverter to get the AND. So we'll get a NAND symbol and we'll get a NOT symbol, this inverter symbol, right? So our symbols are in a way so that the connection in the parents hierarchy. So what's the parents hierarchy? And that is designing a AND. So anytime we wanna design a AND, we don't wanna do everything from scratch. We already have prepared our AND and NOT gate here, and also probably NAND gate in some other day. We'll just get the symbol, connect them, done. That's why it doesn't matter how you just, it should be in a way so that the next anytime you design it will be perfect, like easy. And the one convention, and that is in would be this side, out would be this side, and power will come from top and down. That's the general convention. So here this is my V in. So how I'll copy it? See, it is very, very important, because here we have three things actually: this red dot, this line, and this level. We need to copy all the three together. If you copy one, then connecting them after there is little tough. And these things are the actually cons of using any open source software, because here these things are a little bit tricky. In Cadence, in Synopsys, these things are not tricky, but we are using it for free, so we can at least do this thing, right? So just control, like highlight everything with dragging, and then again see, and see everything is moving. So move it to the location where you want, so it is there. So this is your V in. And also let copy this, because this will give me the name. Here I'll write NOT gate. Okay, done. We can delete this. This is perfect. Let me save it. So it is done. Now what I'll do, I'll design a test bench. Test bench is nothing where we will give the excitation to this inverter to see if it is working or not. So I will again open another one, and let me give it a name. So before that, file, save as, and save as inverter test bench. and you also follow like this only because the final objective of our tutorial is to upload it on GitHub. So for GitHub, it should be a little bit of representative, so that it look good to other, like you are publishing it for the world, right? So there should be good representation. So that's why you also follow something like that only. Schematic, make the symbols, and then do all the simulation in the test bench environment. And this is how we follow in the industry also. So you also do this thing and write it as inverter test, and okay. So inverter test is there, and now I need to get that symbol which I have created. So again Shift I, and this time let me go up. This time I won't go inside my Sky or Xschem library. I'll go inside my library because I already created a symbol. So I'll get it and I'll place it here. A little bigger it seems. Okay, no issue. And then I need to power source again, and V out is already there, V in already there. One option is that we can directly connect through a wire, but that will make things dirty. In a complex schematic you can't do like this. So how we do, we just give the level, the pins here. I will include the pins here, I will include a pin here, so these both things will get connected. But before that, let me make this as V in. So I'll write it as V in. What's the value? Tell me what would be the value of V in. Okay, for now let it be 0. We will fix it. And V out is your VDD. So VDD will be the fixed. We can use any VDD, right? From 0 to 1.8. 0 probably won't work. How we know that 0 won't work? From our previous steps. Episode 2. Try with VDD 0 and give any VGS. You will get 0 output. So from there we know that 0 won't work. Use the biggest number, which is 1.8, which is supported. But hey, this also have some issue, and that is when we'll discuss about power consumption, we'll tell you why giving the biggest possible number is a con. Actually, it's not a good thing. But for today, let's give it the biggest possible, which is supported by this MOSFET, which is inside that, and that is 1.8. So let us give it 1.8 only. And after that I need another ground, another 2 ground actually. Let me copy it here and copy it here, and let me Shift I, let me get the pin, I pin. Okay, so this is one pin, and here actually we can give levels also, because we are not creating any symbols. So let me give the levels here. Left, and you can give any one of them, no issue. Left pins. Tell me what we are missing now. Is it okay? I can run netlisting and simulation. Yeah, so you are correct. We need to define our simulation. What type of simulation we're gonna do here. Also, we don't know about V in. It's error here. We also don't know about V in. What should be V in our? We have given it 0 here. And we are not worrying about anything, because if we give 0 also, in at least it will be 0, but we can overwrite it using our code block, right? So that's why for now we have given it 0. We will decide. So see what today we're gonna do. We're gonna do VTC, voltage transfer characteristics, right? So see, for VTC we do DC simulation only. So today we'll do DC simulation. Transient simulation we will do specially for knowing like rise time, delay time, and also power consumptions. And we'll do those things in the later video. So let us bring a code here. So I copied it from our previous test case, previous schematics. What happened? Yes. So here a few things we're gonna change, and that is library would be the same. Here let us give some fancy name, and that is VTC. Okay. We're gonna do what called DC simulation only. We have fixed our VDS, and that is 0.18. So we will remove it from here, and we're gonna vary our VGS, the input actually. Here it will be input. So we're gonna vary input here. You don't see it, and there's the issue. Yeah, we're gonna vary our input here from 0 to 2 or 1.8 probably, and in a step of 1 milli. So okay, and after that we'll click on netlist. If any issues are there with netlist, we'll get it actually. And we have issues, and that is, see, open net, vout is open, that is perfectly fine, vout is open, and net 1 net 2 are undriven. Why it's undriven, anybody can guess? Yeah, we have done a very silly mistakes, and that is, if we go inside this, let me go inside this, and to go inside a symbol you just need to press E. Save this file, yeah. And here see what the silly mistake, and that is our body and gate, both body terminal are not connected. So let us connect it, zoom in, yeah, it is broken here, so yeah, and then save it, and then to get out of it again, to symbol view, I think it is shift E or control E, yeah, control E will work. Yeah, now let us do again net listing. Net listing is going on, but I can't see netlist window. Why? Because in last video I have said in the option you need to do this, show netlist window, and spice is already selected, and then netlist, and see netlist, it is netlisting perfectly. If you compare your netlist from yesterday's video and today, you will see this is extra, because we are using a symbol. Symbols are like function mostly, like in our general coding sense. So you are using this symbol which have these things. Here you can see one thing, and that is it is getting a x1. Okay, x1, remember x is for if anytime we are calling anything from outside, not in the flat level, in the hierarchy. Here what is happening, in the 0th level we have the MOSFET which will make your inverter, and in the next level we have the test bench. So we are calling something from a below hierarchy, so that's why x1. We will explain what is x1 in the netlist only, and that x1 is got connected in this 4 terminal, perfect, B in, B out, ground, and V out, this, and the name of that x1 is your inverter VTC. So to get a definition, we need to search for the subcircuit of inverter VTC, and if you go down, you will see somewhere it is written inverter VTC subcircuit, and see here in the subcircuit inverter VTC, it is explaining what is inside my inverter VTC, and it also have 4 terminals, and these 4 terminals are got connected to this 4 terminal in the next level. This is the down level where the MOSFET level designs has been done, and this is the test bench level. So it will connect respectively, this bean will connect to this bean. If you made some other name also, it's all perfect, no issue. And here we are explaining everything, that here it have a input pin, and 3 input pin, 1 output pin, and also the device level specification, MOSFET level, what is the W, what are other things which we are fetching from the sky130 PDK. Okay, and then these are my by default. Here I am overwriting V in, because by default, see here V in is 0, what I have given here 0, and this is fixed. So our netlist is perfect. I think you have understood netlist. If not, comment it down. I will make a short video again to explain you netlist again, and I think if you have any doubt, just follow that NgSpice manual, there everything is written perfectly. Save it, and then simulation. I am doing one wrong thing here, one faulty things here, I'll explain a little later. So simulate it, simulation is going on, and it is done. So what we'll do display to see what are the plots are available. These are the plots available, and we are mostly interested in our V out, to see our V out. But before that, let us see our V in plot, or let us plot both of them, V in and V out, and voila, this is what we wanna see. Actually, let me make it bigger. So this red one is your V in. V in is increasing, it is DC simulation, it's not a transient simulation, so that everything is changing with respect to time. In the x-axis it is not time, it is just your steps, how your that input voltage is changing. So it's just that steps, so it is changing from 0 to 1.2 actually. And if you don't appreciate this, then you need to see my that tutorial, interview special tutorial, where in depth I have deal with these things in theory. So you need to appreciate this, to enjoy this, you need to know the theory. So my request would be, if you're not understanding this, please go there, see it, and then come here, you will appreciate it. Okay, so I assume you have you have revised your theory. So now see this point. If you see my mouse, this point is when your V in is equal to V out, and this is actually the threshold when you are from 1 our logic is changing to 0, and in theory it is called VM also. In the book, if I have this book, in this book, if you read this book, this point is called your VM. In my tutorial video also I use it as VM only. So this is your VM. You have a low logic, right? You have a high input output, high 1 means 1.8, and anytime you are crossing this VM threshold thing, your input is high but your output is low, which is the behavior of your inverter. That is perfect. But I am doing a wrong thing, and that is I'll tell you here. So see, NgSpice is a very powerful tool. You can do many things, but we don't need everything today, so we'll only learn what is necessary. So here what I'll do, I want to know this value here. Actually ideally it should be in between 1.8 and 0, in between it should be, right? So it will be 0.9 ideally. If it is 0.9, that is perfect. If it is near to 0.9, then also is perfect, but it is deviating too much, then it is not a perfect, because then what's the issue you will face? You will face a noise margin issue. If you can connect it, your theory are perfect. If not, you know what to do, that tutorial. So that's why we need a symmetrical VTC, but you can see it is not symmetrical. I'll prove you now here. So what I'll do, so we'll use a command which is called measurement. So it is written by MES. So measure a value whose name would be VM, because we're gonna get this, and whose type, like, and that value is coming from a DC simulation. So we'll write DC here, and the variable name is VM, right? And the value of this VM would be when our V in is equal to V out. It's like English language only. And see, this is your VM, and this is in -1, so it is 0.83. Ideally it should be 0.9. It is 0.83. It is close by, but again it is not the perfect one. If I zoom in here, so we want to get it here, so that means you need to get your VTC up, right? If you we come here, probably 0.9 is here, so we need to make our VTC this side. You can say up, or you can say right side shifting, and that can be done by widening your PMOS, and that is what called design mostly. And the fundamental thing what we are missing here, I have done wrong, and that is, see, let me go inside. And what's the width of your PMOS? It is 1. And what's the width of your NMOS? It is 1. It should be minimum, like W by L of PMOS by NMOS should be 2. Best is 3+, but we don't go there because of area penalty. So it should be 2, and that's the mistake I have done. So let me make it 2, and we'll see again like how our VTC is working. And okay, let me do it, save it, and come out. So Control E. Okay, and before that, let us just remember this one. It is 0.83. okay, here -1 is there, that's why I'm calling it 0.83. So it should come little up, like 0.89, 0.88, like something. 0.9 you won't find. For 0.9 it should be more than 3, but in general we don't do that. Okay, so after doing that, I will again click netlist. Netlisting is done. Okay, in netlist let us check if it got changed or not. So I'll come here, and you see you have used 2 MOSFET, M4 MOSFET. One is of this type, and this is your NFET, and here W is 2. Another is of P type, and W is 2. So in netlist where things are getting reflected, so it's perfect. So save it. Now I can't do simulation because this simulation window is running, so I need to close it. So that's why I just remember this one. It is 0.83. okay, and never ever close this one, because if you close it, your Xschem will also go down. So don't close it. So I minimize it. I am closing it. 0.83, remember. Okay, 0.83. Simulate, and here again we'll get that one again. So it's measure from the DC simulation a variable whose name is vm or anything whatever you like, when v in equal to v out, v in equal to v outs, and see it got improved 8.6. it is better than 0.83. you'll get a much improved noise margin now, and in general we use this ratio only. So your task could be, you can keep on increasing your PMOS and try to get it 0.9, and also increase the NMOS and see how your VTC curve will shift down or in the left side, shift up or in the right side. Let us get V out here, plot V out and V in, and see now it is previously it was somewhere here but it moved here, and that's why we are getting a large number. Previously it was 8 point, if I zoom in, previously it was here now, yeah, 8.3 somewhere here, but now it's shifted right side or up to this. Mostly our aim is to get it here, but in general, in practical scenario, in all the practical chip, we don't do that. 2 is sufficient actually. Like for some very specific reason, probably we need a best noise margin, that time we do that thing, that ratio. And I have said noise many times, probably you are just probably you are not appreciating noise. If you know the theory, you might be appreciating, but in our next video for sure we're gonna see the noise margin analysis, and that time you will actually appreciate everything. So for today your task would be increase your PMOS further and see how it move, also do the same for NMOS and see how it move. Okay, and we'll see you tomorrow's video with the noise margin analysis. And you know what you need to do, you need to like this video, comment down, let me know you are here. It is very motivating actually. See you in our next video. Bye bye.